Okay, so normally in these problems, you'll be given a set of functions and constraints on those functions, and you have to come up with the starting perimeter, the starting region. So here I'm actually giving you the region. We'll do it backwards. So this is the function f. This is x equals 1 here. And then also this is going to be part of the region along like this. So can we write a series of statements? First of all, can we write a series of statements that defines all these points inside here? So you had a little practice of that in the area, right? So in your area homework, you had some practice of that. But can you write a series of mathematical statements that defines every point inside this region? Can you do it? Take a minute, see if you can do it. So what should you write so that what you're talking about is, or maybe 2, 3 lines or something like that, that defines every point inside this kind of shark fin region. Take a minute, see if you can do that. So when you organize this or when you set this up, you think about in terms of y and in terms of x. So if we wanted to find those points, what's my y constraint, or what in terms of y? What are all those points in terms of y? I want every single one of these points. What's true about every single one of the y coordinates of these points? Oh, this is pre-calculus. This is graphing and algebra. What's true about the y coordinate of every one of these points? They all have the function value of f? All these points? No? Less than or equal to the function value of f, right? And what else is true about those y coordinates? Nice and loud. Okay, but x-axis isn't a number. Right. So y has to be what? Less than or equal to f of x and greater than or equal to 0. What about x? Yeah. 0 to 1, right? 0 to 1. With also this, right? So as long as we have this as well, we won't get every x value from 0 to 1, just the ones that are in that y range. So we can go 0 less than or equal to x. So when you put those two together, you get all those points inside that region. So in a problem, you might be given something like this. The region enclosed by, so this is just y equals f of x equals 1. And what is this bottom boundary here? How do we say that mathematically? Y equals 0. And then you have to figure out what region they're talking about. So you'd sketch f of x, you'd sketch x equals 1, y equals 0, and then you'd have to figure out what region is enclosed by those. Okay, so that's normally what you'll have to do. Okay, very good. So now let's look at the sheet. So on that first, so what we're going to do now is we're going to take this region, and specifically the perimeter of that region, and we're going to rotate it about the y-axis first. And in that first graph, upper left, that first graph, we're going to try to sketch the shell that we're going to get when we do that. So we're going to take the perimeter, rotate it around the y-axis. That's the vertical one. Rotate it about the y-axis. What shell will you get when you do that? And we're going to try to sketch that before I show it on the screen because you're going to need practice at that. So sketch the shell that you'll get when you rotate the shark fin around the y-axis. You can compare with the people around you. Here's another chance to see what got cut off on the left. So one helpful technique is to sketch the mirror image of what you'll get at half of a rotation, right? At half of a rotation, it'll look like that. And then you can just kind of get a 3D image here. You can kind of make an oval there and an oval down here. Let me try that last part again. That's better. Can you imagine the shell? Can you imagine the shell now? So any questions on that drawing? You're going to have to make drawings good enough for you to solve the problems, right? You have to make, it doesn't have to be artistically perfect, but you're going to be making the drawings. You won't have GC, you won't have the animations for every example the way that I do in lecture. All right, so let's take a look here. Maybe not. Let's see here. Okay. Whiz. So here it goes. No, that's not it at all. Where am I? I'm in the wrong one. Try this. That's the right one. Here it comes. Ready? So this is what we imagine here. Rotating around the Y. So let's take a look here. Now I'm looking at it from behind. Here it comes. Finishes it off. All right, so we start by rotating that perimeter to get an empty shell, right? It's empty. So what is the empty shell? Is it above the gold bowl? Is it like inside the gold bowl above it? Is that the shell we're talking about? No, right? It's below. It's the shark fin, right? It's inside, below the gold bowl and above the turquoise floor. That's the shell we're talking about. So what are we going to do? Our goal is to get a function for the volume as we fill it with shells, right? We're going to fill this thing with shells, and we have to decide what kind of shells we're going to use. And then we want a function for the volume for all points of filling along the way. Okay, so this is what we're going to start with, is we're going to do delta x intervals to start with. So in the middle drawing here, we're on part B. We're going to make intervals of delta x equals 0.2 along the x-axis. And then we want to sketch one cylinder in the interval from 0.6 to 0.8 so that the inner radius is at the beginning of the delta x interval. The outer radius is some value of x as it varies by dx through the delta x interval. And then the cylinder's height throughout is the value of x at the beginning of the interval. So those are your three criteria for sketching this cylinder. Okay? So again, the inner radius is the x at the beginning. The outer radius is like a typical x in the interval. We think about dx varying through the interval. And then the height is the height at the beginning of the interval. So first mark off your delta x intervals of 0.2 and then try to make that cylinder. See if you can do it. Go. And if you have questions, you can grab one of us. This is what we should have been attempting to draw. Okay? So the whole delta x interval is from 0.6 to 0.8. Delta x is 0.2. And then dx is going to increase through that interval. So for some, here's, your x value could have been here at 0.7, anywhere along here, right? So I just threw it here at about 0.65 because dx is changing, right? So this, the cylinder is growing through the delta x interval. But then the cylinder comes from that also being rotated about the y-axis. So when we use, x is our independent variable. X is increasing through delta x intervals. For this particular situation, when dx increases, right? When dx increases, is the radius changing or the height changing or both of this typical cylinder in the current interval, right? We have the cylinder in the current interval. Is the radius changing or the height changing or both? It's growing in radius, right? And then through the whole interval, the height stays constant. Whatever that height is at the beginning of the interval, the height stays constant through the whole interval. So in this case, radius is changing. Why is that important? Why is knowing that the radius is changing important? Because what are we after? Yeah. Right. The rate of change is determined by how our cylinder is growing. Is it growing in height or is it growing in radius? And those are the two cases we worked out. So when the radius is changing, what was our rate of change of volume? And so this will be with respect to x when the radius is changing. So we paid our dues so that we could say that the rate of change of volume is 2 pi RH. Do you remember that? And what is 2 pi RH? 2 pi RH is? Yeah, it's this surface, right? It's this lateral surface, which makes sense because as the radius grows, what's the rate of change of volume? It's going to be like a little sleeve because as it grows out, right? That blue shaded area, the light blue shaded area, okay? So that's going to be our rate of change in this case. Okay, questions on drawing the typical shell? So now I'll show the pretty version of that. Are we good on this, on your drawing? Any questions? So I think that's this one. Yep. So, as you were making these sketches, is this what you imagined? Filling the shell with cylinders of what? Constant height and changing radius in each delta x interval, right? So at the current x value, the radius is growing and the height is staying the same. So what makes this a little tricky is, yes, the height changes from interval to interval, right? When you get to the next interval, you have a new height. But the rate of change function is about what's the rate of change at the current x value, right? At the current x value. And at the current x value, the radius is changing, but the height is not. That's the key. That's what you focus on. What color are you focusing on here? Turquoise, not pink. You're focusing on the turquoise. Those heights are staying constant and the radius is increasing. That's why our rate of change is the 2 pi RH. Okay, so now let's figure out what that is specifically. So our rate of change of, what's our goal? We want to write the volume accumulation function. Now we see this shell being filled, and we want to keep track of how much volume we have for any given x value. How much volume has filled the shell so far for any given x, right? And you can see the x changing here. Here's the x right here. Okay, so our rate of change of volume we said was 2 pi RH. And so now we got to get, so what is the radius? So if I pause things here, I don't need to pause it, I guess. What is the radius of the turquoise shell? It's x, right? The radius is x. So this is this question where we say, is the distance we're looking for, is it an x value, a y value, some big change in x, or some big change in y? So the radius is what? That's the radius right there. It's an x value, okay? And what is the height? The height is right there. Someone said f of x. Therefore, we're right. So if we have the rate of change function, if we got it in terms of x, we can write the volume accumulation function. Volume as a function of x. Who can do it? Go. See if you can do it. Write it down.
It's really hard to know. I'm not sure, to be honest.
Okay, so here's what we're doing. We're in the delta y interval starting at 0.6. Okay, so we've got that value of the function. So that's going to be the bottom of the cylinder, and then the cylinder is going to grow according to dy. The inner radius is going to stay at the starting inner radius. And then the height, the new height will be according to dy. And so then that will be rotated around the y-axis just like the shell was. So we're going to have that like that. And so what will we get? Oh, that's really confusing. So let me try to make that easier. So it looks something like this. That's what I'm attempting to draw there in that delta x interval, delta y interval starting at 0.6. So does that make sense? Right? The bottom of it is at 0.6. The inner radius stays at the starting inner radius, and the outer radius stays at 1. And so what's changing in this as y increases through delta y intervals? The height changes. Does the radius change? No. So these are our cylinders. They're going to fill this shell up. Remember, the shell is that below the blue bowl, right? So below the blue bowl part. So it's going to fill it up, and the height is going to change for each of those cylinders as we fill up the bowl. And so what will our rate of change be? Rate of change of volume with respect to y will be? Remember what the rate of change is? It's the leading face of how it's growing. So we're talking about this is how it's growing, right? This is how it's growing. So what do we say? When the height is changing in these cylinders, the rate of change is area of the base, which is area of that base, that black shaded region. Pi r outer squared minus pi r inner squared. Remember doing that a couple classes ago? We said when the height is changing in these cylinders, it ends up that our rate of change is the area of the base. We've got a hole in it, right? There's a hole in it, so the area of the base is going to be the whole area minus the area of the hole. Okay, so then what is going to be our volume? Volume as a function of y will be integral from? Oh, we didn't figure out what r was yet. So now we got to figure out r0 and ri. So what's r naught? What is r naught? So, or r outer. That's r outer. What is that for these shells? Always 1. It's constant at 1. Never changes, right? Every single one of those shells is going to have an outer radius of 1. They're going to be along this part of the cylinders. Every one of those cylinders, the outer radius will be all the way out to the outside of the shell, which is at x equals 1. So it's going to be pi times, it's going to be pi. And what's the inner radius? So is it an x coordinate, y coordinate, a big change in x, or a big change in y? This is the inner radius. X coordinate, y coordinate, big change in x, big change in y. Okay, yeah, it's a change in x, but you can do better than that. It's from what? It's all the way, the y-axis is the center of rotation. It's from the y-axis out to the point on the curve. Which is? No, not dx. We have dy in this. It's just x, guys. It's just x. The distance from the y-axis to a point on the curve, that's the x-coordinate, right? That's, you start at the y-axis and you go, you do your x-coordinate. So it's just the x-coordinate. It's from the y-axis out to the point on the curve. That's x. So it's going to be pi times x squared. But what's wrong with that? Our function, we need our function in terms of y, right? We need our function in terms of y. So now I'm going to tell you that y is x cubed over 4. Or f of x, sorry. F of x is x cubed over 4. And if f of x is x cubed over 4, that's our y coordinate, is f of x. What do we need? We need x in terms of y, right? We want to write our rate function in terms of y. So yes, it's pi minus pi x squared, but that needs to be in terms of y. So how do we do that? How do we get that in terms of y? If we've got y equals x squared over x cubed over 4 is our function, the blue function. Well, we got to do the math, right? We got to do the math. 4y equals x cubed. So x equals cube root of 4y. And so then our rate of change function is pi minus pi times what? Cube root of 4y squared. Okay, and so then, now we can write the volume function as a function of y. It's going to be 0 to y times the rate function, which is pi minus pi times cube root 4t, right? And that thing squared dt. Which follows our basic form, our structure for accumulation function. Okay, so did I lose you? If I lost you, please ask. Do you follow that? Every semester it takes longer and longer. Okay, so let's look at another example. Good on this example. Any questions? So now I have, this is curved, but it's going to be x plus 2. So this is, imagine that's a straight line. So f of x is x plus 2. Okay? And g of x is x squared. And so we're going to write, so watch here. So am I showing in this animation, am I showing x increasing through delta x intervals or y increasing through delta y intervals? Maybe? Start again. There we go. So y is increasing through delta y intervals, is that right? Okay, and so then what do you notice about this that's different? What kind of cylinders do we have here? Okay, they're all right cylinders, but looking at those cylinders there, and then looking at these cylinders at the beginning, do you notice anything that's different? These don't have a hole, right? So these are like pancakes. So we start with pancakes, and then we change to washers. So if we wanted to write a volume accumulation function for this, what would that require? Writing the volume accumulation function. It would have to be piecewise, right? Is that what you're saying? Yeah, so we'd have to start with, so we're going to start with accumulating the volume according to these pancakes, and that's going to be from y from what to what? Y from 0 to, so this is, f of x is x plus 2. So this is y equals 2 here. So as y goes from 0 to 2, we're going to have pancakes. And so, and those pancakes changing in height or changing in radius? Changing in height or changing in radius?
Radius.
Height, right? In the current interval, the current value of y, what's changing? The height of these cylinders. Okay, therefore rate of change is? Rate of change of volume with respect to y in the first, this is for 0 to 2. It's just going to be the area of that blue base, right? So it's going to be pi r squared. What's the radius? X, y, change in x or change in y? This is an x coordinate, but x coordinate of what? X coordinate of f or x coordinate of g? G, so we'll have pi times x squared. And how do we write the x coordinate of g in terms of y? Notice, x squared. See that? What is x squared equal to? Y. Okay, so that's our rate function for the first part. And then the rate function for the second part will be a washer, right? So we're going to have the pi r outer squared minus the pi r inner squared for these here. And then we'll have to, for the volume accumulation function, we're going to have to construct a piecewise function, right? It's going to accumulate according to the pancakes. And then we're going to get that volume for the pancakes and add it onto For the second part, the accumulation due to the washer stacking up. Okay, so written homework's due Wednesday. It's up. Okay, so you can start, definitely get going on the homework this weekend for Wednesday.